Okay, so today, final lecture, last big idea of the course, which is the divergence theorem. So we're going to take some time to kind of synthesize all the big ideas of the course, culminating with the divergence theorem. We're going to take some time at the end to kind of reflect and put it all together. I have a tendency, and I think most professors do, to like when we complete a course, it's just, all right, we did it. See you next time. Instead of really kind of putting together everything that we have built up, going from start to finish, at least a brief reflection on what we've learned over these last 16 weeks. So I do want to take some time to do that. So we'll have a reflection, kind of Q&A at the end, and we'll do 16.9 to start. All right. So what I want to first do before stating the last theorem is go through all the big theorems we've learned and kind of draw a theme or analogy for you to try to put these together in a more organized way in your brain. So let's just jot these down. Big theorems from calculus. And this is not the only theorems. We've looked at a lot of incredibly important ones, but these are the ones that are all kind of connected together. So the first was the fundamental theorem of calculus, which we learned back in Calc 1 and Calc 2. And what did it say? It said if we have the integral of the derivative of some function, this is equal to the difference of the function's values at the endpoints, okay, at the boundary points. So we can kind of think of it as like I had this 1D region from A to B, right, where that region is really an interval of points. And what did we do? Well, we summed up all the little bits of the derivative f prime on this region. And this equation relates it to the values at the endpoints. So let's say here's like my A and B. Then there was some height f of A and some height f of B. And so this relates the boundary points values of the function to the like kind of net change over the region. Region being an interval, and I'm using that language pretty carefully. The next kind of version we saw of this was the fundamental theorem for line integrals. This had a similar theme to it. It said what? If we integrate over a curve the gradient of some function f dot dr. Well, what's the gradient? Gradient's sort of like a multi-dimensional stand-in for the derivative, right? It's a vector with all the partials of f as its components. So in a way, it is kind of a derivative of f. And this was along some curve C, where it started at P0, ended at P1. We're on some curve C here, and we integrate all the little bits of change, all the little bits of the derivative. And this equation related it to what? The values of the function at P1 minus P0. And so you can think of this as, again, an equation relating the integral of the derivative. And I'm using these heights as kind of a an imagery for just the value of the function. These dotted lines. So it related, again, the values at the boundary points to the sum of all those derivative values. So it allowed us to go both ways on that equal sign. right? Saying that I could either just evaluate the two boundary points, or if I don't know what those are, I could get the net change from just taking the line integral. So I either know about the interior or I know about the exterior, right? And one tells me about the other. So for the next one that had the same theme is Green's theorem. Green's theorem, next dimension up, instead of a curve or an interval, what did it do? It said if I take the double integral over a region D of this q sub x minus p sub y dA, this told us that this is equal to around a closed curve. The integral of the vector field on that boundary, right? So again, kind of here we see this derivative of f stand-in of big F, right? Partial of q with respect to x minus the partial of p with respect to y, which is actually related to the curl, which we hopefully will have time to see today. And the curl is like a derivative of the vector field, right? It's what the gradient crossed with big F, right? So this is kind of a derivative of F on a region D. And this equation relates it to the line integral around that curve, around the boundary curve of D. Here's C. And we're looking at and integrating, the heights, so to speak, of big F. The values of the vector field on the curve on the outside. So again, boundary points moving from endpoints to a boundary curve around a region, right? So the exterior values telling us about what's happening on the inside. There is a equivalent form which I hope to show you how we get it, an equivalent form of Green's theorem. The vector form. It's not a far walk from starting here. But what it says is that the double integral over that region D of p sub x plus q sub y dA is equal to the line integral of f dotted with the normal with respect to arc length. Okay, so just by playing with the notation on both sides, we get an equivalent form for this thing. And this in particular, dp dx plus dq dy, you may recognize it, you may not. This is the divergence of a two-dimensional vector field, right? So this is really div f, which is really, gradient dot f. So looking at this version of a derivative of the vector field on, again, a region D related to what's happening on the curve C around D with values of the vector field. Okay, so the boundary, again, telling us about what's happening on the inside, relating the derivative of on the region to the boundary. And then lastly, we looked at Stokes' theorem, which was last time. And what did Stokes' theorem say? Well, it said the integral on a surface of the curl of f ds is equal to the line integral around its boundary curve, right? Its space curve that maps out its boundary. So it took curl F, which we know is the gradient cross F, on now a three-dimensional surface. And this equation relates it to what's happening on the boundary C. Values of the vector field. And these dotted lines I'm using kind of representing like a bar chart, just the value of the function, but it really could be, the vectors themselves, right? The vector field as you go along the path and summing all those values up, dotted with dr. But this is like a rough stand-in, just to visualize it. So, it's kind of like, we can judge a book by its cover is like the weird little lesson that we're learning here, right? That if you have information about the boundary, that will tell you about the interior of the region, and vice versa. If you know about the interior of the region, that can tell you about what's happening at the boundary. And so the divergence theorem is another emanation of that. And so that's where we're heading. So one thing I want to do is I want to actually at least partially derive this form of Green's theorem. This is something from 16.5 that we didn't cover then because we didn't have some of the mechanisms that we have now. So first, deriving Green's in vector form. So if we take a look at this, and if this doesn't land with you, it's not a huge deal, okay? But I do want to walk through it. So if we start with this line integral over C, again, remember Green's is in 2D, okay? So it's around the boundary curve of a 2D region. So if we start with this on a closed curve C, the vector field dotted with the normal with respect to arc length. Okay, so what's kind of the work being done, or rather, what's the component of the vector field dotted with the normal, so going perpendicular to the surface. Okay. And so what this ends up being, if we parameterize it, is big F dotted with n at t where we've parameterized the curve from A to B for t, and this here we'll hold on that thought for a second. And so if we make a big substitution here, so I'm going to make a leap and then I'll explain the steps. So swapping some things out. So I'm dotting F. If we remember, F is Pi plus Qj plus Rk, and these are all going to be given by t now because t is giving me the x, y, and z components. And we know that this guy here, since the tangent in 2D is given by derivative of x over the magnitude of the vector function I plus derivative of y over the tangent vector. This tells us that n is what? It's going to be normal to that. So what are we going to do? We flip and negate the components, right? So this becomes instead y prime over r prime I minus x prime over r prime j. So I know that's not obvious, but it just takes a moment to kind of reflect on that and make sense of it. Okay, so if t is pointing in the direction of the vector, or the curve rather, the space curve, it's tangent to that curve, Normal is just swapping and negating the x component there. So why we need this is because if we dot the normal with the vector field, this is what we end up with. It's a big, long expression. P, where the components are given by x of t, y of t, times y prime of t, all over magnitude of the tangent vector, minus q of x of y, x of t, or x prime of t, all over magnitude of r prime. Reason that's nice is because we're multiplying by that magnitude of r prime, so these things cancel. So it does get a little bit nicer. So then, okay, I've got p of xy times y prime of t minus q of xy times x prime of t, all dt. And if we move into, we can remove the parameter by calling this dy dt and calling this dx dt. Then we can drop the dt and just move into a more compact form, where this is p dy minus q dx. All right, so you have these dt's will cancel here. Now here you can use Green's theorem to move this into a double integral over d of p sub x, so dp dx plus dp dy, because of the form that it's in. And this is the divergence of f, and that's where we get that from. So this vector form of Green's theorem tells us that over a closed loop, this is equal to the double integral over d of the divergence of f dA. So if we go around the border and add up what's shooting through that boundary in the normal direction, we add all that up, that tells us about what's happening in terms of the outflowingness of the vector field on the inside, right? So we can kind of gather all the data on the border instead of having to drop infinitely many points on the inside. So this is nice. We're going to kind of mark this alternate form of Green's theorem, because, and hopefully, you know, I've trained you to at least ask the question, what happens when we take this up a dimension, right? This is in 2D. So the question is, what happens when we go up a dimension? Well, what would that look like? Well, instead going from a 2D region, and actually I want to switch these around for a moment, because this is how we wrote the other ones. So let's rewrite this like this. This was kind of our convention up above. You see what I'm saying? With the integral of the derivative on the left and the boundary integral on the right. So looking at now the summing up the derivatives on the interior of the region. Well, this is a 2D region. So if I take that up to a third dimension, I'm talking about a solid now, right? So if I can add up all the divergence inside a solid, what would tell me about that on the boundary? Well, we could talk about the double derivative of the double integral of the vector field at the surface, right? What's passing through the surface on a solid versus what's happening on the interior. So you might posit here what if the triple integral over some solid region E of the divergence of F dV, is this equal to the integral across the surface, which is a boundary, right? What's the boundary of a surface? What's the boundary of a region, a solid region, right? It's a surface around the outside. And this turns out to be true. Under certain conditions. E must be a simple solid region. No holes or weirdness there. It has to be a type 1, 2, or 3 region. And that S, or this delta E, I think you've seen this before, this is the boundary of the region, must be a closed surface. And that our normal vector n is positively oriented outward. So we have to keep our handedness going in the right direction. So this does that by keeping n. If you're looking at a solid, the normal vector's positive direction is outward, up and out. All right, so the concise way to write this divergence theorem, is exactly this, just the triple integral over E, divergence of F dV is the double integral on the surface of big F ds, with all these conditions implied here. It's also called Gauss's theorem. And if you go to Eastern Europe, they call it Ostragradsky's theorem. Depending on who you talk to. The French and the Russian folks tend to call it Ostragradsky's. So what does this really mean? Well, this means, and I'm kind of reading this backwards, the flux of the vector field, right, which is what the volume of flow per unit time, right, the volume of the fluid per unit time across the boundary of E, the region, is equal to the triple integral of the divergence of F. I'm actually going to write it as divergence. Which, again, you can think of divergence as outgoingness of F over E, the whole region. That's really what this means. So we've got the derivative through the solid being related to the flux over the surface. So it's in theme with those other theorems that we've looked at. Okay. So the proof of this is not beyond any of you, but I'm going to reserve it for the super nerdy and curious. So there is a proof of a special case of this. In general, it's a little bit beyond the scope of this course. But if you're curious, if you're a math major, you're going on pure mathematics, definitely check it out. But we're going to kind of just rest on the intuitive definition for now and kind of this theme that we've seen building up through all these other theorems. So let's work an example and we'll show you how it's useful. It's very similar in its applications to the others, but obviously with higher dimension, it means that there's going to be more that it applies to. One of the biggest ones is to find a flux integral. So if we have this vector field over the unit sphere, well, how could we possibly use the divergence theorem to help us here? Well, what does it say? It says the divergence of F dv inside a triple integral is equal to the flux integral. So flux integrals can be a lot of work. Sometimes it's easier to go ahead and calculate the triple integral with the divergence through the whole solid. And if it's a relatively easy 3D region, right, 3D solid, even better. So the unit sphere, not too bad. That's just x squared plus y squared plus z squared equals 1. As the sphere, that's the boundary. So then let's go ahead and think about, well, if the surface is just the shell, then what is the region E that's enclosed by that shell? We call that the unit ball. Right? Ball versus sphere. Ball is solid. It includes all the interior points. So that's x squared plus y squared plus z squared less than or equal to 1. All right, so we have a rough idea of our region. We need to figure out the divergence of F. And it might have been a while since you've computed this. Remember that this is the gradient dotted with the vector field. So we're really just taking the partial with respect to x of z plus the partial with respect to y of y plus the partial with respect to z of x. Which works out to be 0 plus 1 plus 0. So this isn't too bad of a vector field. Its divergence is 1. Remember, this is going to be a scalar measure, not a vector. It's telling you how much things are outflowing from given points. And that could depend on the point that you're at. Here, it's a constant amount. Okay, so you can think of the rate or the amount that vectors are pointing away from the center of this vector field is constant. So the divergence theorem tells us we've got enough to go on. This flux integral is equal to this, which is equal to triple integral of 1 dv, which is really just the volume of the ball. We'll call that E. And what's the volume of a sphere of radius 1? 4/3 pi r cubed. Radius is 1, so we've just got 4 pi over 3. So easier than computing the flux integral for sure. And all we had to know was what's going on the interior of this solid in terms of the derivative of the vector field, right? The divergence, how things are changing. So let's do another one that's somewhat similar. This is, I would say, 70% of problems lend themselves in this way, that a volume integral can be easier than a surface integral to compute in terms of setting it up. So computing a flux integral using the divergence is the most common that I see, at least, in terms of just pure computation problems. So let's evaluate this flux integral where big F is xyi minus a half y squared plus zk hat. Oh, where's my j hat here? My surface S consists of the surface 4 minus 3x squared minus 3y squared from z equals 1 to 4. This is like the top. Z from, we've got the cylinder, x squared plus y squared equals 1. This is for z values 0 to 1. These are the sides of this. And z equals 0. This is the bottom. So don't need to sketch it, but this thing does look like a silo. Okay, we've got a upside down paraboloid on top of this cylinder, and our base is this disk at the xy plane. All right. So that's the surface as the boundary of this whole thing. So calculating this flux integral, we'd have to break it into kind of 3 parts for this surface. Where instead, we could get away with using a triple integral of divergence and grabbing all of that inside to tell us about what's happening at the surface. So we'll use divergence theorem. We'll say that E is really this solid where we've got a disk D in the xy plane that's radius from 0 to 1. We've got theta ranging between 0 and 2 pi. And then we know our Z height stops at 0 at the base, and up top here, these values are given by this surface. And we want to stick to polar, so we're going to have to convert this here to be what? 4 minus 3 r squared. Hopefully we've done this enough to see what happened from here to here. So we've got E. We're going to need the divergence of our vector field. So our vector field is this guy up here. So partial x is y. Partial with respect to y on negative 1/2 y squared is just minus y. And partial z at the end is plus 1. So again, we're left with a divergence of 1. This doesn't always happen, okay? But in the interest of trying to move through a few examples, we're speeding it up. So divergence could depend, and often does, on where you are in space, right? It's a measure of how much vectors are flowing away from that point. Sometimes it's constant like this, but not always. So then divergence is 1. So that means that this is equal to divergence of F triple integral dv, which again is 1 dv, which is the volume of E. Well, the volume of E, we should be able to set this up. We have our inequalities, 4 minus 3r squared for r dz dr d theta. All right, that's my dv piece. So we integrate first with respect to z from 0 to 4 minus 3r squared, so we just get this here, r times 4 minus 3r squared, dr d theta. Distribute that r through. A couple power rules here. Did this not get up? This gets ticked up to 3. Here we go. And then this is between 1 and 0. Moving a little quick. So then we've got what? 2 minus 3/4. So we've got 5/4. D theta. It's 5/4 times 2 pi, which is which is 5 over 2 pi. So what does this tell you? Well, it tells you the total amount of divergence inside the region, but it also tells you about the flux at the surface. Okay? So that's what this divergence theorem tells us. You've got one mapping to the other. So what I wanted to do is make some time to let you guys practice doing this on your own, because obviously next class session is the exam, so I want you to be able to have a chance with me to ask questions on it, and setting this up. So let's do a you try problem here. Use the divergence theorem to evaluate this flux integral where vector field is given by yx squared I hat plus xy squared minus 3z to the 4th j hat plus x cubed plus y squared k hat. And S is the surface of the box All right, so it's like we got a box screen detector measuring the flux, and it's set up between -1 and 2 for x, 0 and 1 for y, and 1 and 4 for z. So let's just say set up the integral, and we'll compute it together. It's not too bad, but obviously the setup is the challenging part. So set up this and evaluate it using the divergence theorem. If you have questions, obviously just unmute, fire away. All right, so wherever you're at, that's fine. Here the region E, the solid box, is pretty much given to you, right? You've got a set of limits for your x, y, and z, so that's good to go. Your vector field's given in, it's a bunch of power functions, so the divergence is not that hard to compute. So we should get 4xy for the divergence. Again, it's just the dot with the gradient and the vector field. And then when we go ahead and compute using the divergence theorem, you can break it up since you've got three integrals that have rectangular regions, right? You can break it up twice using that property of integral. So since they're independent, break them apart. You should get 18. You can verify that. But any questions on that? Setting it up, firing it off? Not too bad, right? So again, this is one of the main uses for it, is finding a simpler way to deal with flux integrals. So I'm going to talk for a moment about some applications of this. Now, again, physics is something that I'm interested in, but you got to remember I'm a pure math guy. All right, I went for complete theoretical. So this is at the boundary of my comfort zone when it comes to physics is these things. But what we know about the divergence theorem and its widespread uses, its most prolific uses, are in fluid dynamics, which you can understand, right? Wanting to know about fluid within a container, how much is crossing the boundary versus how much is contained within, and the relationship there. Electromagnetism, talking about charge contained within a space, and quantum mechanics. And again, all of these are related using the divergence theorem because they have laws of conservation, which you looked at some of Maxwell's equations yesterday or last time. Conservation of mass, energy, momentum. So the divergence theorem helps generate the differential forms and the integral forms of those equations. So one big one that we can dive in a little bit deeper into is Gauss's law. And what it says is that the flux of an electric field, E, across a surface S, which is closed, right, is the total charge enclosed by S. So it is easy enough to show for a simple case how this works when there's just a single charge. If you place it at the origin and you surround it with any surface, that you can calculate how much charge is within the space versus how much flux from the electric field is coming across the surface. If you introduce more than one charge, it becomes very difficult. Okay, but we can start with one, and this rule holds up for multiple charges, but you can't prove it easily. But you can show for when you drop a charge at the origin that this holds up. And so what we see is that the integral across the surface of the electric field dot ds is equal to the total charge contained in S. And so this piece here is really the integral of all the divergence, the outflowingness, the charge pouring through the surface. Okay, but that's Gauss's law in a very much a nutshell. Okay. One that we can unpack a little bit more is in terms of fluid flow. And see a little bit more why we call divergence divergence. So if we think about a velocity field of a fluid, or V, and let's say we have a constant density of this fluid. And we say, let's let this vector field F be equal to the density times the velocity. So this is really the rate of flow of the fluid per unit area. Let's take some point P naught in the fluid, and we'll take a, let me write this in, and a ball B sub A with tiny radius A around P naught. Then for all points P in the ball, they're close enough that the divergence measured at each point is roughly the divergence at P naught. And this again is because divergence is continuous. So there's not going to be some crazy jump. This is a sort of derivative of the vector field. So when we're inside a tiny ball around a point, the divergence is roughly the same as long as it's a very small neighborhood. Then the flux around the sphere, right? So the shell of this tiny ball, using the divergence theorem, well, that's going to be equal to the triple integral of the divergence in that region, which we know then must be approximately the divergence at P naught which then must be just the divergence at this point times the volume of the ball. And as A approaches 0, this gets better and better. So what this tells us is that the divergence at this point, if we divide both sides of this from here to here, this equals 1 over the volume of the ball times the flux integral. So this gives us the net rate of outward flux per unit volume. That comes from here, per unit volume. And this is why we call it divergence. Okay, so you take the flux integral, and it's and we divide it by unit volume of this tiny neighborhood around each point. And so that's where that name divergence comes from. So what it tells us is two things primarily. If you take the divergence at a point P, and it's positive, that means that the vector field is essentially flowing away from that point. I'm going to give you some visuals to help with this, because I know I've just been using my hands and drawing on this thing for a bit. But it's flowing away from this point. So we call this a source. Meaning that there's outflowing from this point. And that div F being negative, we call P a sink. All right, so gravity attracts inward. So if we had a mass at the origin acting on another body, there'd be a sinking force. It's moving inward instead of outward. All right, so again, the importance of the normal vector's positive orientation. So we know what we're talking about. Is this a sink of flow, or is it a source of flow? All right, so let's move to, and we did look at some of these a while back, but I want to refresh ourselves here. So if we look, this is the vector field xy, so this is in 2D. From, and I'll keep the path out of here. So moving outward from the center, this has a positive divergence. So at any point, it's actually a constant 2, which makes sense. At any point, you got to think about how many vectors are leaving the ball versus coming into the ball. And for any place here that I put it, it's going to be the same in and same. It's going to be more leaving than coming in, right? So that tells us that there's a positive divergence. And we see there's no curl because there's no tendency for this to rotate about the z-axis. If I switch things up a little bit, in this vector field, wherever I put this ball, the amount of vectors coming in are the same as the amount leaving. So this has divergence 0. There's no net change. If I switch it up, and I'll let you guys play with this. Again, this will be in the notes. This is variable. It depends on where we are. This is actually kind of hard to see in this example. Let's switch it up. So here we have variable divergence depending on where you're at. Here, the divergence is 1, meaning this is a source. There's more vectors leaving here than entering. And over here, it's the opposite. This is a sink. There's more vectors entering this space than leaving it. And there's also, here's curl being represented at this point. A tendency for vectors to want to spin this point in space if there's a little disk with paddles on it. That's what we're talking about when we say curl. These are two, again, kind of analogs for the derivative, the gradient cross with F and the gradient dotted with F. All right. And then in here, you can also drag in a curve so you can talk about the work done if you'd like based on different types. This is a pretty neat little applet. And then lastly, I had one pulled up in 3D where we have a vector field negative x, y, and z. And you can try to get a sense of, what is happening inside this body, this solid region E. Are there more vectors entering or leaving? It's unclear. We could calculate this. It would seem from the diagram that we have more entering, even though some are leaving out the sides. It seems that more are coming in from the top and bottom. Again, this is really hand-wavy way to talk about divergence. You can calculate this exactly, but This is the visual representation of what it means to have positive or negative divergence. And if we just had something like, actually, that's not going to be good. All right, like this, here's this outflowing vector field, x, y, z. This obviously has positive divergence. And if we flip all these inward, this is a sink, so it's got negative divergence. This is kind of what we're talking about. All right. All right. Questions so far? All right. So that's the divergence theorem. It connects the flux at the surface to the divergence inside. Talking about the relationship between the boundary and the interior. So what I wanted to do was take a quick moment and kind of summarize the big ideas of the course from my perspective. Then I have a quick exercise I'd like to kind of hear from you guys on what you've learned, what you're taking away from this class. And I've got a quick little survey to do there. And then kind of what's next in the mathematical landscape. There's probably a lot of you going on into the STEM world. And for those of you interested in kind of pure math, I can kind of point in the direction of where that would head. So, kind of in summary, and this is obviously not going to be exhaustive. You guys have learned a lot. But the big idea that we just went over is, relating a cover to its contents. Kind of this strange underlying theme of the fundamental theorem of calculus, saying what's happening at the boundary tells us about what's happening on the interior, in reference to the rate of change and then the actual values of the function. But some other smaller ideas, and I've beat this one to death today, so we're going to leave that where it is. Some other smaller ideas that are probably just as powerful is the power of vectors. Right? Breaking things into components. The power of vectors and representation. How now you're kind of armed with these tools that really trivialize a lot of geometric problems. Armed with vector multiplication, the dot product and the cross product. So these things can simplify complex situations. And so you've been given the gift of multidimensional understanding, and now you can analyze things in this way. And not many people get to this point, right? Most people stop at single variable calculus or before. So to be able to think in multivariate is really it's a sad truth, but it is reserved for those who kind of get to this place. And there's other ways to get there through other sciences perhaps, but to really think multidimensionally is a powerful tool. Another kind of interesting thing that happens in this course, it doesn't happen in other classes, is traveling up in dimensions and traveling down in dimensions. Some things port, some things don't. Right, so for example, the cross product. There is a general form of the cross product which is called the exterior product in higher dimensions, but the cross product per se is unique to R3. To be able to generate a vector that's orthogonal to 2 is something that just happens in R3. You can't do this in R2. You can't do it in R4. So it's kind of interesting. The other kind of powerful piece of that, in particular with the cross product too, we saw the cross product was, let me jot this down, anti-commutative. Right? So this property of multiplication and addition that I seemingly, after so many years of teaching, still struggle to get across to folks, of this fundamental property of addition and multiplication, that you can switch the order of things and it doesn't matter. And then we get to a course where, hey, it actually definitely matters the way that you multiply, right? That A cross B is actually the opposite of B cross A. All right, so I couldn't possibly tell that to anybody in my intermediate algebra class right now. But why I bring that up is because this is the beginning of some really advanced mathematical thinking where you're looking at the power in abstraction. So, we kind of start you off with basic arithmetic, number theory, how these things play together. But now you can start to question things like, what does it mean to add? Multiply. Are there operations that are not commutative? Yes, there are. Are there operations that are not associative? Yes, there are. And you guys have probably seen that with matrix operations, quite possibly. What does it mean to be a number? What is a number really defined to be? That is actually, there's two schools of thought on that, which is insane. Okay, so the more abstract you get, we start questioning these basic assumptions, and there's a vast depth of research and people working on fundamental questions like this. Okay, where you're headed is, if you continue down a pure mathematical lineage, would be to move into the field of mathematical analysis. That's where Calc 3 lives. There are other branches that subsume everything else you've learned up until this point. There's abstract algebra. There's topology, which subsumes all geometry. There's number theory, arithmetic, and then there's these crossovers between fields like algebraic topology, differential geometry, are these kind of burgeoning areas of research. And again, these are at the most abstract, and the power lies in the fact that they are most certainly true because they're based on rigorous proof, and that means their applications can easily port in as long as we find that place, right? Whereas a world of applied math is more trying to express physical truths in a math framework. The pure math world is it is truth, right? And it's independent of reality. And so you guys are kind of at this nexus of peering over the ledge of going into applied mathematical uses or pure mathematical. And so that's just a really cool place to be. And I just wanted to highlight that for you guys. And I'm happy for you. So you're kind of like on the beach looking out at the ocean of a wide world now that the kind of multivariate space has been opened up to you. So congratulations, way to make it this far. That's amazing. And I think you guys have done really, really well in sticking with it this semester. So again, proud of you, infinitely so. And here's the summer. We're right around the corner. So a couple last things I would like to do. I'd like to hear from you guys. I'm actually going to turn off the recording now because I think that's all the content for here. Yep. So I'm going to shut that down.